It's mysterious and wondrous. Welcome to the world of relativity. This video will first explain fundamental concepts such as space-time coordinates, inertial reference frames, and linear transformations. Grasping these concepts is essential for correctly understanding special relativity. We live in a universe composed of 3 dimensions of space and 1 dimension of time. Objects move through space-time, with time always moving forward and positions in 3-dimensional space constantly changing. The position of an object in space-time can be represented by 4 numbers, t for time and x, y, and z for spatial coordinates. This is what we call 4-dimensional space-time. Physical space-time is 4-dimensional, but for convenience in visualizing and discussing problems on a plane, we often ignore the spatial y and z axes and limit the object's motion to the spatial x-axis in practical analysis. Naturally, we construct a 2-dimensional Cartesian coordinate system using the time axis and the spatial x-axis. When an object moves along the x-axis, its trajectory in the space-time coordinate system is a line. If an object is moving with constant velocity, its trajectory in the space-time coordinate system is a straight line. The space-time trajectory of a stationary object will also be a straight line, but this line will be vertical. The trajectory of an object in space-time is called a world line. It's important to note that a world line is a space-time trajectory, not a spatial trajectory. The spatial positions of the objects corresponding to these world lines always move along the x-axis. Even if the world line is a curve, the object is still moving in a straight line along the x-axis. While the straight line motion is with varying speed, its world line in space-time appears as a curve. A world line is the path an object takes through space-time. More broadly, a point in space-time is called an event. It represents a specific time and place. In the context of physics, world lines and events refer to certain physical realities. Observing the same world lines and events from different space-time reference frames will show them in different positions and shapes. We usually associate a reference frame with an observer. If a coordinate system is constructed with a space-time event O as the origin, and Alice always remains at the spatial coordinates 0 point, the coordinate system will typically be referred to as Alice's reference frame. Assuming Bob moves to the right at a constant speed along the x-axis in this reference frame, the origin of the coordinate system is the event where Alice and Bob meet. A different space-time reference frame is constructed with this event as the origin, and Bob always remains at the spatial coordinates 0 point in this reference frame. This new coordinate system is referred to as Bob's reference frame. Alice and Bob each view the world through their own reference frames. Let's illustrate Bob's world line in both reference frames. In Alice's reference frame, where Bob moves to the right at a constant speed, his world line appears as a slanted straight line. In Bob's own reference frame, since he remains stationary at the spatial coordinate 0 point, his world line is simply the time axis. Similarly, we draw Alice's world line in both reference frames. The event where Alice and Bob meet, Alice's world line, and Bob's world line, are all objective physical realities. When we draw them in different reference frames, they will appear in different positions. More generally, for an event E that occurs at space-time coordinates x, t in Alice's reference frame, what would be the space-time coordinates x prime and t prime of the same event observed in Bob's reference frame? Newton and Einstein provided different answers to this question, known as the Galilean transformation and the Lorentz transformation, respectively. Before discussing these specific transformations, let's understand inertial reference frames, as both the Galilean and Lorentz transformations are coordinate transformations between inertial reference frames. we can construct countless reference frames in spacetime. Let's observe the motions of objects free from external forces in different reference frames. If their world lines is straight lines, meaning they remain stationary or in uniform straight line motion, we call such reference frames inertial reference frames. The concept of inertial reference frames is crucial. From this concept, we can deduce that both the Galilean and Lorentz transformations are linear transformations. Let's explore the logical reasoning process behind this. Objects free from external forces remain stationary or move in uniform straight-line motion in all inertial reference frames. Therefore, the world lines of objects free from external forces are straight lines in all inertial reference frames. Coordinate transformations between reference frames will convert an object's world line from one reference frame to another. If the object is free from external forces and both reference frames are inertial, then both world lines must be straight lines, meaning the transformation must convert a straight line to a straight line. And a coordinate transformation that maps straight lines to straight lines between two reference frames is mathematically known as a linear transformation. Linear transformations follow a standard form. Any coordinate transformation adhering to this form will map straight lines to straight lines. Further, if the xt reference frame and the x' t' reference frame use the same event as the coordinate origin, the translation term can be ignored. The pre-relativistic Galilean transformation adheres to linear transformation principles. The Lorentz transformation in relativity, though a bit more complex, also follows linear transformation principles. We will discuss its derivation and physical significance in detail in later videos. The Galilean transformation is simple. If you're not familiar with matrix multiplication, we can write it out directly using equations. Time elapses consistently across all reference frames, which is the foundational assumption of the Galilean transformation. Based on this assumption, the transformation formula for spatial coordinates can be easily derived. Here, v is the velocity of the observer in the target reference frame relative to the observer in the source reference frame. Let's return to the world of Alice and Bob and demonstrate the Galilean transformation. Apply the Galilean transformation to events and world lines in Alice's frame of reference. Bob's world line transforms into the time axis, while Alice's world line becomes a slanted line. The spacetime coordinates of event E also change accordingly. Alice's frame of reference becomes Bob's frame of reference. We can similarly use the Galilean transformation to convert Bob's frame of reference into Alice's frame of reference. How to perform coordinate transformations between different spacetime reference frames represents our fundamental understanding of spacetime. The Galilean transformation is simple and aligns with our intuitive understanding of spacetime. In contrast, the Lorentz transformation in special relativity intertwines time and space, presenting a completely different perspective on spacetime. We will explore these concepts in more detail in upcoming videos.